Right, so here's a good place to start. Scientific method. This is something that took people like thousands of years to come up with and formulate. But now we have a systematic approach to answering questions about the physical world. So start off with some kind of question you want to answer. I should say to different textbooks that might have slightly different versions of this. So let's pick the pretty common version, right? Some kind of question you're trying to answer. Uh, background research, how has this question been addressed in the past, what different angles have people taken, what considerations did people have in the past, what conclusions did people come to with what however they set their experiments, some hypothesis, say educated guess, if you can express it like if then, like if I change this variable by this, right, how does this other variable respond? The more you can quantify that, the better. Right, experimentation. Right, so there's the heart of the scientific method. You'll have some setup where ideally, if you can, you would just want to change one variable at a time, the independent variable, and maybe have one variable that changes the dependent variable and leave everything else controlled. Now in this class, like this classroom with the physics experiments, we've been pretty well able to do that. Now in the real world, sometimes the real world can be a little bit messier. For example, if you go into economics, there might be a lot of variables. It's kind of hard to have things really well controlled. But in this class, we tend to do that. Leave everything controlled except for one independent, one dependent. Okay? Analysis can come in different forms. Version that might involve like as already established equations or graphs. Ooh, we do lots of graphs in this class. Right? Graphs, you can at a glance figure out what kind of relationship do you have, like a direct relationship, an inverse relationship, some kind of parabola going on. Right? And then a conclusion, which in this class, physics oftentimes comes in the form of an equation, right? So now you say this variable is related to this variable with like this expression. And then so now you have predictive power. You say, well, if this variable changes by some proportion, then here's how something else should respond. Okay. Right. 7 base SI units. If you want to measure anything we can possibly know how to even possibly measure in the universe, you can relate everything back to these guys here. And really, in this semester, if you've been paying real close attention, only the top three we've ever really dealt with so far in this class. Now, these four on the bottom, some of these I'll talk about next semester briefly. But so mass measured in kilograms, distance length, displacement measured in meters, and time measured in seconds. You might say, well, what about something like volume? Well, volume is just length times length times length, right? So meter cube. What about something like force measured in newtons? Oh, well, that breaks down to kilogram meter per second squared, right? So far in the semester, we really just deal with like these three guys right here. Speaking of those three, let's look at history of those. Here's the original definitions of these. We're talking about, of course, the metric system, which comes from France in about the 1790s. These were the original definitions of these things. Right? Now, the modern definitions are based on universal constants. They get away from physical objects, right? But they're roughly equivalent to these values right here. Right? Ooh, common measuring tools. Right? So you guys have used almost all these in this classroom to measure, well, see those variables and units. You guys know AP makes a big deal out of this, right? Likes to do like scenarios involving students measuring things, or would ask you like what measuring tools could you use for like this particular setup to address this particular question. So definitely know this for AP because you're going to be asked questions about this, right? We now two that we have not worked with for sure are voltmeter and ammeter, volts and current for electricity. I'll briefly do that with you guys next semester, but that's not going to show up on your guys' AP exam. AP lectures. Oh, here are universal constants. This goes a little bit beyond the scope of this course. Some of these slides do, but good to know. No, so these are like unchanging. For example, the speed of light, as far as we can tell, speed of light through a vacuum appears to be that number universally everywhere. Right? The modern definition of a meter is no longer tied to something to do with like proportions of the Earth. It has to do with how far does light travel in some small interval of time, and time is, well, just the reciprocal of right, this frequency here. Okay, so scientific notation. Here's a good way for expressing either extremely large or extremely small numbers, like many orders of magnitude, large or small. Another thing that scientific notation is good for is to clearly establish how many digits of precision do we have. For example, mass of the Earth. Okay, we got 5972. Those digits are like known values, but and a lot of these zeros are just placeholders. We're just okay, it's just like so many crazy kilograms. Right? But what about like this zero right here after this two? Like, do we know that zero is a zero? Is it significant or not? Well, if I just list out the number, it'd be ambiguous, right? But if I write in scientific notation, you can know for sure. And according to how I typed it, it would be just a placeholder, not significant, right? So do we know it's like a 0 versus a 1 versus a 2? Well, maybe any of those. But if I write the number 0 right here, well, now I'm saying I do for sure know that level of precision. Okay. There's 1,000 bubbles. So kilo is a factor of 1,000. Milli is 1,000th. Suppose it's like a raffle prize and you pick one ticket, you have a 1 in 1,000 chance of winning. Kilogram, millimeter, right? 1,000, 1,000th. Here's SI prefixes from milli to kilo. That's probably good to know before you graduate high school. Most of these we use. Class, here's some examples, right? Here's a bigger expanse of SI prefixes from pico to tera. And a lot of those you guys probably know because we organically use these in class, right? Kilogram, kilometers, the other time, megas, a million, millis, micros, 1 minute. Right? Good to know too. Oh, hey, look, here's yesterday's activity. I'm gonna go modify this and add a little bit of precision to that. Right, you guys got analog calculators going there. Accuracy and precision. Accuracy is how close to the true value. Precision is like how many digits deep you go. I got a precise value of speed of light here on the right as an example. More precision going up, right? All your measuring tools have like some kind of limitation, right? And that's a good thing to keep in mind too, right? There's only like so precise and so accurate. It could be like when you get, I guess just like a philosophy of like measuring things, right? Is how like accurate and precise can you get, right? Okay, I'm calling this one dimensional analysis. Now there is a wider application dimensional analysis too, but this is more of a unit conversion example. Okay, suppose you want to convert it. I mean, how often in class, this has been a really useful method, right? Have I said, let's break out some railroad tracks and convert this to this, right? Let's say RPM to radians per second. Boom, we got something. Okay. How many years is equal to a billion seconds, right? Something like that, right? Well, 31 years, they go. Right? Here's another example. I think I had you guys solve this one earlier this year. Suppose you have something like, hey, I wonder how much land area it would take to meet energy demand with nothing but solar. That's a question you can also make a back of envelope calculation to get a pretty good ballpark idea what the answer would be. Right? You're seeing the answer right there. That there's a setup and how you do that. Right? I mean, that's a good skill, right, to have before you graduate high school. There's how you do that. Right? Now, of course, there's some engineering complications to that too that aren't quite shown there, but they give you a ballpark idea to pretty accurate answer. Oh, scaling. So if you scale up something by some factor, different properties change by different factors according to different dimensions. So here, do you guys see this small box in the bottom left? Well, if I blow that up by a linear factor 3 times wide, 3 times deep, 3 times high, and that's that huge crate, right? Well, different properties change at different rates. Anything linear, of course, changed by a factor 3. But anything to do with area, like paint the surface or a shadow that lands on the ground, well, that's a 2-dimensional concept. So take that scaling factor to the power of 2. And now it's 9 times. Right? Anything that's 3-dimensional, volume, mass, weight, occupies 3 dimensions. Right? That's 3 dimensions. So take your scaling factor, put it to the power of 3. In this case, it's 27 times. Right? One example that you guys saw this was if you scale up or down the size of a planet. Right? If you make a planet bigger or smaller, say like different mass ratios, different radius ratios compared to say like Earth. Right? What if you have on a planet that's like half the radial size of Earth and half the mass? What would the gravity field be on the surface, right? And you can use the scaling to, okay, we're going to navigate these different proportional relationships to compare it to Earth gravity. Okay? Algebra. Right there is a pretty comprehensive algebra example. I mean, you guys use this almost every single day in this class. If you felt any bit rusty on this in algebra, then definitely not by now, because we're doing this all the time, right? Algebra right there. Right? Got lots of order of operations. Right? Graphs. So here's a linear graph, y equals mx plus b. Right? In fact, the very last graph on your very last lab was this graph right here. You guys remember it was torque versus angular acceleration. The slope, which here I have labeled m, but the slope for you guys was rotational inertia, and the intercept was frictional torque, right? That was last graph you guys saw in the last lab, right? That one really common, see all over the place. Right. Oh, here's some more graphs. Right. Pretty much all the graphs that you guys are seeing in all the labs is like somewhere on. I mean, it's one of these, right? So there could be no relationship between 2 variables, which might be either a horizontal or a vertical line. It could be a vertical line too. Right? Direct relationships are really common. Y equals mx. Inverse relationships: one variable increases, the other decreases. For example, mass and acceleration for Newton's second law of motion, F equals ma. Lots of parabolas you guys see in this class. Parabola and root are just, you just flip the axes and go from one to the other. Right? The one, I don't know if you guys have seen sinusoidal in this class, not, but you'll definitely see it in January. January, we're going to get into oscillatory motion, like pendulum swinging back and forth. So this one will pop up if we haven't come across this one yet, right? Sine, cosine graphs as a function of time. Okay. Right, there you go. So know those. Obviously, there's more than just that in the wider world, but those are the ones that you really care about for this class, right? So focus on those, know those, right? Quadratic formula. I recommend that you memorize that if you haven't yet. I don't think AP would expect you to, or I would really force you to either, right, to necessarily memorize that, but good to know before you graduate high school. Doesn't hurt to know that, right? For example, let's say you take a ball, throw it straight up in the air, and you want to know at what times does it cross like the third story of the building? It goes way up and comes back down. Well, there's two answers to that because the ball crosses the third story on the way up and also on the way down. And in fact, height versus time would look like a upside down parabola. So two answers. You could answer it with the quadratic formula. Okay. Ooh, circles and spheres. Good to know these properties. I really think you should know these two yellow boxes: circumference of a circle, area of a circle. Right. If you want to expand your knowledge, next step, how about spheres? What's the surface area of a sphere and volume of a sphere would probably be good to know. I don't think AP would expect you to necessarily memorize that, but good to know. Right? Speaking of properties of circles, this is one of the labs I had you guys do. I planned for this to be one of the first labs, and we ended up shuffling it a few weeks into the school year. Remember, I had you guys measure properties of circles. What's the radius? What's the circumference? If you like take a string, wrap it around it, and measure the string. And also, like, if you put it on a grid paper, count the number of squares to represent pretty close to how much area. I had you guys make some graphs. These are 3 graphs that came out of that lab. Circumference versus radius was a direct relationship. And it should come out something like circumference equals like 6.28 times the radius is the circumference equals 2 pi r. Right? Now, if you did area versus radius, you guys remember that came up to like a parabola shape, right? And what would the equation of that parabola be, though? Well, now that's a really tricky question to answer. And how you can figure out the formula for a parabola, though, is you can use a process called linearization. You guys remember that, linearization? We've linearized lots of graphs in this class, right? So if you take radius in that axis and you manipulate it by squaring it, so now it's not area versus radius, it's area versus radius squared. Now that does line up in a straight line, and it's really easy to get the slope of a line. You just do rise over run. So whip off the slope, and then, oh, look at that. You guys see that these two equations are exactly the same? Area is pi r squared, area is pi r squared, right? Now, here's a parabola version, here's the straight line linearized version, right? They both tell the same story, just different points of view, right? It's a lot easier to make the equation by linearizing. That's the purpose of linearization, right? Whip off the slope of a path. Ooh, triangles. You guys seeing triangles all over the place in this class. Different reasons, right? So Pythagorean theorem Pythagorean theorem only applies to a right triangle, a squared plus b squared c squared. There was an expanded version. Do you guys in a math class learn something called law of cosines? I don't think I've quite applied that with you guys in this class, but it's like kind of like Pythagorean theorem, but applied to like not necessarily right triangles, right? Area of a triangle could be 1/2 base height. And if we're talking about right triangle, you could use the 2 legs as the base and the height, right? You guys use that all over the place. Vector components, right? This is something that never goes away, right? You see this all over the place. Now, when you learn this in a math class, you probably learn sine, cosine, and tangent, like the definitions are the ratios of these sides of a right triangle. The application in this class, you just rearrange that a little bit. How this usually works for this class, like 90% of the time or more, is that you'll know some vector, I'll call it C, some magnitude at some angle. And I have to figure out the components. How much over, how much up, right? Well, if you know C and theta, I can say the side B opposite of the angle is C times sine theta. And the side adjacent, A, I'll call C times cosine theta, right? You guys probably apply that like literally over 100 times in this class, right? And then, furthermore, I told you how to extract this angle if you have lots of side information. You can do some kind of inverse trig relationship. A common one is inverse tan of the ratio of the legs. Right, we'll tell you that angle. Right, so all that. Here was a lab you guys did. You did measurements, you did calculations. Oh, look, they all lined up. You guys remember that lab? Okay, now we're to kinematic motion. By AP's book, this is unit 1. Unit 1. This is both linear motion and also projectiles. What do we got here? We got displacements, time. We got velocities. We got accelerations. Boom. Right, different versions of those. Right. One of the first big labs you guys did was car and incline lab. You guys rolled cars down inclines and said, what kind of relationships are governing that motion? I think I divvied you guys in like 3 or 4 different groups to test for different type variables, control some things, variable other things, right? And here's all the graphs, right? So distance versus time, well, there was a parabola relationship, right? And we could make the equation by linearizing it. That's this one right here. I made this one yellow and yellow because they kind of go together, right? Based on the same data, right? X versus t squared. Now that one lines up, which confirms that x versus t is in fact a parabola, right? In fact, x versus t squared is the slope of this 1/2 a, right? Because x equals 1/2 at squared, right? You didn't know that at the time, but you know that now in retrospect, right? The slope is 1/2 of the acceleration, and you have to know that for AP because AP could ask that question. What is the slope of x versus t squared? Oh, well, it's half of the acceleration. Right? If you did velocity versus time, I gave you guys some speed gates. That linearized, so that's easy to make an equation, right? Y equals mx, v equals at. The slope is acceleration, right? Acceleration would be constant, right? Got that? Right? So many guys swapped out the mass of the car. Like you taped lab weights to the car is what you did. So you had a blank car, then you had like heavier and heavier cars, right? And what you found is that had nothing to do with the motion of the car. So mass was independent of how much time it took to reach the bottom, right? There's no relationship, right? And then if you did v versus x, that came out like square root. That reminds me of v squared equals 2ax kind of deal, right? So you could like linearize it like that. Right? All right. So that was a that was a pretty good lab right there. It's a lot of physics right there. Right? Right. Then look at so scenario: car drives at constant velocity, and I have set up 3 graphs: distance versus, or I should say, displacement versus time, velocity versus time, acceleration versus time. Right. How many of those sets of axes are in your notes? I mean, it's all over the place in your notes because so many times I said, pull out your notes, do x versus t, v versus t, a versus t, and I kept throwing you a bunch of different scenarios and said, what does that graph look like? What does that graph look like? Right? You should be able to construct this set of 3 graphs for any scenario that's thrown at you because we've done a ton of them in this class. Right? Here's a really basic example. Car drives at constant velocity. So I-95, just driving north toward Jacksonville, just constant speed. Just, right? That's exactly what these graphs would look like. You're picking up displacement at a constant rate. That rate of changing displacement is called velocity. It's constant. So now if there's a constant velocity, your speedometer's pointing a constant number. Right? And the rate of velocity, the time rate is acceleration. And there will, of course, be 0 acceleration because that's what constant velocity is. Right? Boom, boom, boom. Right? There's some equations. You guys can figure out those. All right, so now let's bring in acceleration. Now there's 2 kinds of acceleration. There's speeding up, slowing down acceleration called linear acceleration. Oh, look at that, rate change of velocity per change in time. Right. Now later on, a few weeks later, we did the acceleration involved with going around a curve, like changing direction. That's called centripetal acceleration, but that was like a unit 3 concept. So that one didn't come for a while. Right. So let's just focus on this linear acceleration. Right. Right. That brings us to these 3 kinematic formulas right here. Right. Now if you keep a track, there are 5 different variables we're juggling, right? Time, acceleration, displacement, initial final velocity, right? You guys remember, if you can identify any 3 of these things, kind of get to the next slide, right? In principle, if you can identify any 3, the other 2 become solvable. They can become locked in place. If you only have 1 or 2 variables, then it's not solvable, right? Oftentimes in physics textbook, some of these variables will be implied or they won't explicitly express a number. For example, if anything, quote, starts from rest, unquote, then you know v naught is equal to 0 meters per second. Okay? If anything breaks to a stop, you know that means final velocity is 0. If anything is in free fall, then you know acceleration is, well, you might have to assume that you're on Earth. Okay, well, it doesn't explicitly say that you're on Earth, but that's a pretty good assumption. So acceleration in free fall is probably 9.8 or 10 meters per second squared, right? Okay. And then you can apply, of course, these formulas and blah, 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 right? Let's look at, say, drop a ball off a cliff, right? Now, this is a lab I did not do with you guys, but this is a pretty classic lab, could have, right? Suppose you drop a ball, starts at rest, there's a kinematic variable, and you know the height it falls, boom, there's a second, and how much time, boom, there's 3 kinematic variables, right? V naught, x, and t, right? You can, in principle, solve for gravity field if you assume constant acceleration, right? So you could do that. You should get, pretty close to 10 meters per second squared on Earth, right? All right, now let's go to a really tall cliff. Let's say edge of a cliff, drop a ball, and it takes like 5 seconds to reach the valley below. That's what that picture is, right? Every second took a picture, right? Right. So here's a table with all the kinematic variables on it, right? So time, ticking along 1 second at a time, right? Oh, look at the acceleration. It's constant. It's picking up 10 meters per second per passing second. That's called 10 meters per second squared, right? Of course, we're ignoring air drag. We usually do in this class as a simplifying assumption. Okay. And then what's going on with velocity? So release from rest, 10, 20, 30, 40, 50 meters per second. Hey, look at that. It's picking up 10 meters per second every passing second. Now, the kind of tricky one is displacement. Let's see if you guys get this. Guys, edge of cliff, drop a ball. How far does it fall in 1 second?
5 meters.
5 meters. Ah, right. Can't trick you guys. 5 meters. Because the equation that goes with that is 1/2 AT squared or 1/2 GT squared, right? So 1/2 times 10 times 1 squared. Yeah, 5 meters, right? How about the old mine shaft? Ooh, I wonder how deep it goes. Drop a rock. Takes 5 seconds to hit the ground. I wonder how deep it is. How deep? About 125 meters. That from 1/2 GT squared. How'd you know that? College. Yeah, college. That's the answer. Right? Oh, here's the graphs. Table, graphs, table, graphs. It's the same story, just different ways of representing the story, right? Ooh, I sure do like these graphs. Yeah. Displacement versus time. There's a nice parabola, right? Velocity versus time. Ooh, it's increasing at a constant rate, right? Like v equals gt, right? And acceleration versus time is constant. Boom, boom, boom. Right? If you know any one of these three graphs, the other two become pretty well locked in place because they're all related to each other. Let's look at those relationships. The rate change of displacement is called velocity. You guys see how, like, if you hold your ruler flush to this parabola, the slope is always changing, but it's changing at a constant rate. That's v1, v2, v3, v4, v5, right? Changing at a constant rate. Oh, then if you plot those velocities, hey, they all line up in a straight line, right? That's an instantaneous rate change. What's the calculus term for that rate change? It's called what? Derivative. Right. And then same thing from V to A. The rate change of velocity is acceleration. Oh, look, I've labeled that slope. I call it G for gravity field, right? And that is a constant slope. Therefore, the acceleration is a constant value. Look at there. And that's another derivative. You can also go the other way. If you accumulate acceleration times time, that's a change in velocity. So it's change of velocity at a constant rate. Oh, change at a constant rate, right? And then the area under V versus T. Well, see, I'm getting triangles. There's a small triangle, bigger triangle, bigger triangle, right? The fact that we're getting triangle shapes under V versus T means that X versus T opens up to a parabola, right? And that's what's the calculus term for that? Finding areas under curves. Integration, right? Integration. When you guys eventually do that in calculus, that's what it is. It's just the backwards process of differentiation, right? What if you don't drop the ball? What if you throw the ball? I can throw it up or down since we're still in linear motion, right? Both of these sets of graphs are defining down as the positive direction, right? Therefore, if you throw it upward, you're throwing it into negative territory. And look at this maximum height, right? Notice that corresponds to exactly 0 velocity, which makes sense too, right? In fact, that's how you can find maximum height. If you're ever asked, you throw a ball straight up, something about maximum height, right? You might have to recognize that one of the kinematic values would be 0 velocity at the maximum height point. That's how you would find that, right? My earlier AP class told me that you guys had not yet in calculus gotten to optimization. You haven't done optimization yet, right? When you guys get to optimization, you guys are looking at it right here. I might say, like, what is the maximum height? Ooh, okay, so I'm trying to maximize something, but minimize something. It would be the same principle. It's where the slope of that value goes to 0, right? That's exactly how you find some kind of maximum or minimum, right? So now you guys can optimize. Boom, done. Right? Throw a ball downward. Oh, hey, look at this graph right here, V versus T. You guys know the area under V versus T, of course, represents displacement, right? V versus T is very, very information-rich graph, right? The slope is acceleration, the area is displacement. Let's blow that up. Boom, now it's big. I have a trapezoid shape. That's a triangle sitting on top of a rectangle. Rectangle is V naught T, triangle is 1/2 AT squared. So the total displacement is V naught T plus 1/2 AT squared. Hey, that's the first kinematic formula, right? Here's the equation of this line. V equals V naught plus AT. Hey, there's another kinematic formula. Speaking of which, let me scroll back to those kinematic formulas. I meant to mention this too, right? Did I have you guys take the time derivative of the first formula? Guys, what's the time derivative of displacement called? Velocity, V naught T. If you take the derivative with respect to time, you get what? V naught, 1/2 AT squared. What's the derivative of that? 2 times 1/2 this way. AT. Hey! Look, the first formula, take the derivative, you get the second formula. Woohoo! Yeah, it's calculus right there. All right. Reaction time. You guys remember doing this? Right. So how do you figure out reaction time? Well, you can't really use a stopwatch because that's kind of what you're trying to figure out. Hey, I know what you can do. 2 friends drop a roller, that guy catches it. You can say, how far does the roller fall? And then you can take this formula, you can rearrange it and solve for the fall time, right? I think that would be a pretty good AP question, right? That could be a multiple choice or an FRQ, right? Might be a kind of a simpler FRQ, right? So one common mistake I see is students mixing and matching different units. Guys, if the ruler falls 17 centimeters, for example, you catch it at 17 centimeters, can I plug in 17 for H and 9.8 for G? Will that give me the right answer? No, you get a way too long reaction time. I can put in 0.17 meters and 9.8 meters per second squared, or I can do 17 centimeters and 980 centimeters per second squared, right? But I have to have common units. So careful about that, common mistake. Right. Oh, here's the table for it. Right. Oh, car brakes to a stop. Car brakes to a stop. You guys have gotten this scenario lots of times, keeps coming up, right? It'll show up and here's kinematic motion. In dynamics, it's going to come up. In energy, it comes up. You guys remember something about like conservation of energy, starts with kinetic energy, goes to, you guys remember that, right? This is a really common scenario in this class. Here's what the kinematic graphs look like. X versus t, upside down parabola, v versus t. We're assuming, of course, a constant rate that slows down. Right? And then acceleration versus time is a constant negative value. Okay. Here's some formulas. The displacement notices this triangle, which is 1/2 v naught t. Right. That's a pretty good one to know. Right. You guys see just the area of a triangle is how far it goes under v versus t, I should say. Right. How about stopping distance in terms of acceleration? Is hey, if you cross multiply this 2a, isn't that v squared equals 2ax? That looks a heck of a lot like that third kinematic expression. Right? Velocity and acceleration on a table. If they're both positive, that means moving forward, speeding up. If they're both negative, that means moving backward, also speeding up. Right? If the signs are mismatched, like a plus and minus or minus and plus, then you have a slowing down situation. You're slowing down backward, you're slowing down forward. Right? Now projectiles. We're still in Unit 1 by AP's book, so kinematic motion. But now we're thinking in 2 dimensions. Suppose we're on a plane, blast a cannonball, pow, out it goes. You could ask different questions about this. I wonder what's the maximum height of the cannonball? What's the how far downrange does it go? Right. Regardless of the question, you start out the same way. But I'm gonna split this velocity into components: how fast across the field, which is of course constant, and how fast leaving strictly upward, which is an initial value because then gravity immediately starts pulling down, and then it goes into this parabola shape. Okay, parabola path. Right. Blast a ball at the edge of a cliff. All right, you guys did this lab. You guys remember this lab? All right, let's look at its motion. Now that's a parabola right there. Right, and then what's going on horizontally, vertically? Horizontally, you guys see how like per unit times equally spaced, x equals vt horizontally, right? But vertically, oh look, it's like spreading out as if you just dropped the ball, right? It's like spreading out. There's your y equals 1/2 gt squared, right? And then put it all together, you get a parabola. The question I asked you guys on your lab was, can you calculate the blast speed from the launcher if you know the height of the cliff and you can spot where the ball lands? And of course, you're also allowed to know gravity. Okay, right? Hey, there it is right there. Right, there's a spot where the ball lands. There's horizontal motion in green. Right, here's the height of the cliff. Something about it falling. H equals 1/2 gt squared. You can solve for time and do a substitution, and boom, there's your answer. Right? That would be a really good FRQ question. Like if AP asked that as an FRQ in May, I think that would be a really fair question. Okay, could you guys solve that from scratch? I think you could. There's the answer on one page. There's a table for it. Range formula. Ooh, hey, look, it's all tie-dye. I always like that. Let's go back. Okay, this is a little bit extra, maybe beyond the scope of this class, but where does the ball land as a function of, say, throwing speed, gravity field, and the angle that you throw it, right? Maybe that's a pretty good one to know, though, right? The derivation for that takes a few pages of paper. I think I uploaded that as a bonus video, I think, if I remember right? You could also use this too. If you throw a ball, you know the angle you throw it and you spot where it lands, you could back calculate how fast did you throw it. Ooh, that'd be pretty good too. All right. Let's go on here. All right, let's go to Unit 2 by AP's book, Dynamics, Forces, Newton's Laws of Motion. Right now, here I put mass. I haven't mentioned mass very much so far because mass does not show up in those kinematic formulas. You guys remember mass regularly cancels out. In your car and incline lab, some of you guys were changing the mass, but it just showed that it canceled out anyway. Right? But now mass matters because we're going to introduce forces. Forces cause accelerations. A force acting on a mass, that's Newton's second law of motion. F on m equals a. Right? Back in kinematic days, we were saying acceleration is a rate change of velocity. Now we're saying how you get it. You get it by applying forces. Right? Here's different kind of forces. Put tension way down here. Right? You guys remember coefficient of friction has something to do with the ratio of friction to normal force. Right? And then I got spring constant here. How stiff is a spring? Right? 1 Newton to measure force breaks down to 1 kilogram meter per second squared. Hey, that's F equals MA. Look at that. Okay. Pressure, pascals, that's like force per unit area. So Newton per square meter, break down to. Newton's laws of motion, first law of motion, called the law of inertia. Object at rest, stay at rest. Object in motion wants to maintain its velocity, that's speed and direction motion, right? Unless there's an external force acting on it. Guys, anything that is ever speeding up, slowing down, or going around a curve, there has to be a net external force on that object. And that net external force will produce some kind of acceleration. It might be a linear acceleration. It might be a centripetal acceleration. We're talking about Newton's second law of motion here, right? Net force on mass results in some kind of acceleration. Now, when I say net force, if an object has like 10 different forces on it, you have to sum those forces to figure out like as if there's a single force, right? And that net force divided by mass tells you the magnitude of acceleration and also the direction. It's the same direction. A lot of times it's written as F equals ma. I like the fraction form myself, right? And it's third law of motion. Forces always come in pairs. If there's two objects pushing or pulling on each other, pushes or pulls, those are forces, right? Then there's always an equal and opposite force setup, right? Forces always come in force pairs. Right? Two different objects. You have two different objects pushing or pulling on each other. There's also Newton's second law, third law of motion, a different view of that. Right. Hooke's law, we're talking about springs. You can compress or stretch a spring. Now, your guys' spring scales were like stretchy springs, right? You guys remember that? Right? If you put a force on a spring, it'll stretch it by some amount. How much? Well, it depends how stiff it is. That's K. So F equals Kx. Some textbooks throw a negative sign in front of that, call it F equals negative Kx to represent the restoring force. I left it off, whatever. Right? If you look really close, there's a second spring formula down here. If you look at the area under F versus X, I see a green triangle. That represents the energy stored in the spring. You call it spring potential energy. You could also call that the work done to like stretch or compress the spring in the first place, the work done doing it. So that's 1/2 kx squared. So notice that's two different formulas that represent two different things with two different units, two different concepts. Force measured in newtons equals kx. That's that black line, right? Energy stored in the spring or work done to stretch it in the first place is 1/2 kx squared. Okay, that's measured in joules, right? Now that's a unit 4 concept. We haven't quite got to that yet, but remember, it's two different things, two different formulas. In January, we're going to have an oscillating formula with springs. So that'll be another formula of springs. Right? Okay. You guys did lots of lab activities with springs. Free body diagrams. We're going to label all the forces on an object. You could also say all the moments or torques on an object. We didn't get till recently. So right now we're looking at forces. Notice velocity vectors are not part of free body diagrams. Sometimes I'll draw it for context, but it's not actually part of the diagram. Right? For example, right there. Rocket in deep space at constant velocity. You guys remember I had you guys draw all different free body. I gave you guys a bunch of scenarios and said in your notes draw force vectors. Right? You're looking at the answer right there. There are no forces on that rocket. Why is it in motion? Because of inertia. Ooh. All right. Well, there's the bell. So, all right, we'll pick up there next time. Right. You guys have a great weekend. See you next time.